This is problem 14 from chapter 17. The problem reads, for one approach to this problem such as this, see multiple concept example 3. The problem reads, sound emerges through a doorway as in figure 1710. The width of the doorway is 77 centimeters and the speed of sound is 343 meters per second. Find the diffraction angle theta when the frequency of the sound is A, 5,000 hertz, and B, 500 hertz. So first things first, the equation we're going to be using is sine theta equals lambda over d. And we know to use this equation because it tells us that it's a doorway, and we can assume that doorways are rectangular. So this is the equation to use when we have a rectangular area or surface. But the first thing we have to do in order to solve this equation is calculate our lambda, and we use this equation here. Lambda equals velocity over frequency to determine our lambda. And as stated in the equation, they give us our velocity, and they also give us our respective frequencies. In A, the frequency is 5,000 hertz, and in B, the frequency is 500. But when we solve for our frequency in part A, we find that our wavelength in part A, we find our wavelength to be 0.07 meters. So once we calculate our wavelength, we simply plug it in to our equation there, and we obtain the value for theta of 5.2 degrees. And in part B, we do the same process, whereas we solve for our wavelength by dividing the velocity, which is the same, by our second frequency, which is 500 hertz, and we get our wavelength to be 0.686 meters. And we do the same thing as above. We plug our wavelength into the equation where we have, in both cases, our d is the same, 0.77 meters. But we plug in our value of our wavelength, and then we take the inverse sine of that to get an angle of 62.99 degrees for our angle theta in part B.